Oh, hello, welcome back to stochastics process. And then today we will check in the classification of states. So let's start with the first definition. Definition one. We have the accessible. Let x n a stochastic process of n greater than or equals to 0 be a Markov chain with state space x and then state j is, so we say state j is said to be accessible from state I if we have the probability of moving from I to J over n step is greater than 0. Now, like from some n greater than or equals to 0. Is that okay? So we state J is said to be accessible from state I if the probability transition from I to J over n step is greater than 0. If it is equals to 0, that means that it's not possible to move from state I to state J. But if it is greater than 0, then there's a probability of moving from state I to state J. It can be over the first step, the second step, the third steps, however. So from this also, we can also get another definitions, which are called definition 2, and that is the communication definition. We say two state ij I, j communicate. So take note of this: communicate if they are accessible to each other. If they are accessible from each other. That is the probability transition moving from I to J over n step is greater than 0, and the probability of moving from J to I over m step is also greater than 0 for some n, comma m greater than or equals to 0. So I will write this: communicate as I come accessible by J and over J. While for the accessible alone, we will write this I and with this arrow pointing to J. That is, J is accessible from I. So, but with these two double-edged arrow, so that means that denotes communication. So J is accessible from I, and I is also accessible from J. So we say that those two states communicate. So let's check this example for better understanding of this classification of state. Example, we have the question: are the states in the following Markov chain accessible from each other? In other words, accessible from each other means they communicate. So let's share this transition diagram. And state 1, state 2, state 3, So we have 3 here, we have 4, and then we have stage 5. So from 1 to 2 to 4, and 4 to 2 other. So we have 3 to 4, we have 3 to 1, then we have 2 to 3, we have 4 to 5, and then we have 5 to 4. And we have 5 communicating back to himself. And I have 2 communicating back to himself. So if you look at this example now, I'm going to example 1, you will see that the probability of moving from 1 to 3, that is from 1 to 3, is still possible if you take this route from 1 to 2, then from 2 to 3. So that is just that it is over 2 steps. That is, before you can move from 1 to 3, you first of all move from 1 to 2, then from 2 to 3. So if you also check the other way around, for example, the probability of moving from 1 to 4. 1, you move to 2, you from 2, you move to 3, from 3, you move to 4. So that is 1, 2, 3. So that's over 3 steps. Is bigger than 0. So you can see that there's a probability of you moving from one state to the other in this Markov chain. So we can agree that this Markov chain is accessible from each other, they are accessible from each other, and they communicate. State 1 communicates with state 2, that is from 1 you can move to 2, and from 2 you can move to 1. That is from 1 to 2, then from 2 you move to 3, then you still go back to 1. That's over 2 steps. If you move from 1 to 2, that's over step 1. But from 2 to 1 is still possible, it is over step 2. Also from 1 to 5, you can see that you move from here to here, from here you move from state 1 to state 2, state 2 to 3, state 3 to state 4, and state 4 to state 5. So it is possible to move from state 1 to state 5. It's also possible to move from state 5 to state 1. That is from 5 you move to 4, from 4 you move to 2, from 2 you move to 3, from 3 you move to 1. So this Markov chain, we can agree that it's accessible from each other, and we can just say that the Markov chain communicates. Is that again? Alright. So let's take some theorem under this communication. So the communication is an equivalence relation and they possess 3 properties. Number 1, we have reflexivity. For any state, I, so we have for any state I, we have state I communicates to itself. So in church, we can see that each compartment, each state communicates to itself. So church, we call it reflexivity. Then 2, we have symmetry. And if I X communicates to J, then we can also see J communicates to I, vice versa. So we have transitivity. transitivity, transitivity. So we have if I communicates to J and then J communicates to K, then we can say that I communicate to K, and this is where we derive the common graph equation. You can check our previous video in common graph equation. Okay, so with that, I believe we should be able to move to irreducible and non-reducible, and I will take you to definition 2 and definition 3 rather. Definition 3, well, a Markov chain is said to be irreducible if it consists of only one communicating class, and that is all states communicate with each other. So just like the previous example, this example 1, we see that all states communicate with each other. Then we call church Markov chain to be irreducible. I'll take note of that. So another definition, definition 4, is a communicating class C of states is said to be closed if it is not possible and to leave that class. So, and that is if you enter a particular state or a particular class, it is no longer possible for you to get that from that class. Example, look at this transition diagram. Then you move to this side. Same. So this is a closed communication within these 4 states. So in this state they are exclusively closed, and then it cannot move out from this particular 4 states. So you move from here to here, from here to here, from here to here, you go back here, you move here, then you go back here again, you move here, you move here, you move here. So it they're just in the circle. There's not moving out from there to another state. So this will also help us to have a definition of another type of state, which is called an auxiliary state. So we say a state I is said to be an absorbing state. Is said to be an absorbing state. If I, that is state I, is a closed class. That is, once we enter I, you remain in I. The probability of going back to I is 1. So that means that there will not be any transition. The probability of moving from I to I just over 0 step is equals to 1. So the probability that is going to move from that state I to another state, it is 0. So with that, now you have to also check this definition 6. It says state I is said to be recurrent and if probability of moving from I to I is equals to 1, or transient if the probability of moving from I to I is less than 1. So if there is a probability that you can move out from that state to another state, that means that is a transient state. But if the probability of moving outside from that state is 0, but the probability of moving from back to that state is 1, then you have a recurrent state. So you have to take note of that. And then in our next video, we'll be checking other types of the classification of states we have. So but before then, let's check one example in order to drive this concept better. So let's take this as example 2. It's example 3 now. Consider a Markov chain consisting of 5 states. State 1, state 2, 3, 4, 5, and having the following transition probability matrix. So you have 0.4, 0.3, 0.2, so 0.3, you have 0, 0, 0, 0, so you have 0.6, you have 0.4, you have 0, 0, 0, you have 0.5, 0.5, 0, 0, 0, you have 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. Alright, these are transition matrix. So we want to check if it is the following transition probability. So now we have to ask to determine which states are recurrent and which ones are transient. So let's take one after the other. The probability transition of P of I to I 1 to 1. So from 1 to 1, don't forget it's 1, 2, 3, 4, 5. Next 1, 2, 3, 4, 5. So 1 to 1 we have 0.4, which is less than 1. So this is a transient. Probability of 2 to 2, 2 to 2, that's 0, which is less than 1. So this is a transient. Okay. Probability of 3 to 3. 3 to 3 is also 0, so less than 1. So this is a transient. Probability from 4 to 4, that is also 0, which is less than 1. This is also a transient. And the probability from 5 to 5 is also 0. So this is a transient. So all the 5 states we have, they are all transient. So there's a probability of moving from one state to the other. Is that okay? So here we stop for today. My name is Sunday. Thank you for watching and hope to see you in the next class.